So let's talk about functions. So we are at the chapter 3. We're gonna introduce functions, not just the single variable function, multi-variable function, and also we're gonna talk about how to graph the functions. So let's talk about what is function first. So how do you define a function? What is a function?
Defined with variables and
Say it again.
define the formula with
Formula.
variables.
Variables. Okay. Formula with variables. Okay. I'm gonna write it right here. Formula and variable. Yeah. So usually it's expressed as a formula and variable. This is the way of describing a function. So you can also think there's no problem thinking of function as this way, but how would you define a function then? What is function? What comes to your mind when you hear of word function?
Something that takes input and gives output.
Yeah, something that inputs and output. How about you?
A little bit similar to him.
Mm-hmm.
I think function is like a tunnel that
Tunnel.
change x to y.
Okay, so some kind of this picture, like a black box, so you put the x and you get output y. Right? Yeah, that's true. So function, so formula and also this kind of picture, let's say function f, is giving you an assignment rule. So it consists of assignment rule. Right? And is it enough to define a function? Yes, do you need a variable? That means you need to know from where you take the values of variables. Yes, domain and codomain, right? The domain and codomain. Sorry, codomain. Okay. So this seems like too formal, but it's really important. Whenever you want to draw or you want to explain a function, you have to think about these two pieces of information. So usually we just take the assignment rule and domain. The codomain follows from the assignment rule, right? Because you know what the output variable is, so it depends on what input is. So it's dependent on the input variable. So this y is dependent variable actually. The name of this variable as output variable is dependent variable. This is independent variable. So if you really need to make it concise, the information about function, then you can keep the domain information and assignment information because codomain information follows from these two. And so let's think about ways to express the function. I think we can now use this one. So how do we express functions? So I will just keep one way of expressing function here. The formula is a nice way to express function. And I think this is exclusively all the method you learned in high school to express functions. But what other method do you think is possible to explain a function? Graph? Yes. Others? Label? Table, yes. Okay, the table. Any others? Any other?
Just writing down values.
Yeah, words, yes. Can anyone think of others? There could be more. If it's not, that's okay. So, why is formula always comes first when you describe a function? For example, when you think about function, you probably think about this kind of notation, and f of x usually represents some kind of formula in terms of x. Why does it always come first? Yeah, you use it in the high school to solve problems. And do you think it's really useful out of your school boundary? Like if you're dealing with a function every day, every time. For example, everything you do is a function. You want your cell phone to work. Like you tap on some part of your screen, you want your cell phone to work. That means you know the function, how your cell phone works, right? So how do you describe the function in that formula? That function as a formula? Well, you can't, but you can explain by words. So if I press this button, I know that something will happen. I know what will happen, right? So you can explain by words, most of them. And you can also explain by graphs. That's a one way. And also sometimes in high school, we use the graphs just to understand the formula, right? And graph is, you can see the graph every time in a news or textbook, whatever. They never put the formula to explain a function, right? So if they say, okay, so there was some increase on the population of our country in these years, they put the table or graphs. They don't put the formula in, right? So its formula is not really useful outside of your school boundaries. So let's talk about these four methods. So, no, not formula itself. So let's talk about the graphs. How do you graph the function? What's the definition of function? A definition of graph. How do you define a graph? Oh, it's gone. Where is my? Okay. How do you define a graph? Well, yes. Right. So, yes. So let's talk about single variable functions. So you have two interval. If you want to graph a function, this single variable function, you want to set the two-dimensional plane, right? But we cannot put the infinite plane on a finite board. So you have to restrict the size or window of your plane, right? So that restriction will be determined by domain and codomain, right? So in this box, you want to do something, and you want to put basically points, right? Points. So these points, x, y, which follows the assignment rule of the function you have, right? So when you connect all the points, it will be a line. But now, if you want to visualize the graph, you cannot put the infinite points. Impossible, right? So what do? Connect to points, right? So if you want to look like a curve, then you put lots of points, but not infinitely large, just finitely many, but not distinguishable by bare eyes, so that it looks like a graph. So so today I'm going to take your advice on the screen. So I'm going to show you how to graph the function, the single variable function here. So let's say I want to draw y equals to x squared. So x goes to x squared. Let's define a function and let's import the package called matplotlib, pyplot, and well, also let's import the numpy. And what do? So in order to take a point, I need a lots of points in my interval. So let's say my interval is from 0 to 1. So then I need to get lots of points in between 0 and 1. So I'm going to use linspace. And without third attribute, let's say I have 5. That means I will have interval 0 to 1, split it into 4 so that I have 5 points, including left and rightmost points. Okay. And then y is going to be the compute of x. So in this code, what happens is I just put this numpy array straight into the formula, and when I take the numpy array squared, it's not the matrix square, it's just the square of each entry in the numpy array. So that I'm going to have the same size array for y and plot x and y. So this is the figure you can see. So you can see there's a break. So it's a sharp corner here, right? Because I have 1, 2, 3, 4 splitting of my interval. So if you want this nice smooth curve, what do? You take a lot more points, right? So here 5 means it's the number of total entry of the array. So I'm going to get rid of this. That means I take 100. 100 is the default. So I get nice smooth curve. So if you enlarge this figure, then you will see that there are lots of 99 line segments joined together to look like it's a curve. It's not really a curve. So now let's talk about other type of functions. So this is something you're probably familiar with. So our course title is the multivariable calculus. That means we need to work with the multivariable function. So here I'm going to show you, let's take a definition here. So two variable function. I can define n variable too, but let's start with a two variable function. F of x is a function that maps the points x, y in a two-dimensional region to a value or point. Okay, so the reason why I'm saying this is that sometimes your value of function is just the value. So which means that it's just the real number. But sometimes your value of function is a point. Could be a two-dimensional point or a three-dimensional point, right? So this is inside of three-dimensional space here. So this value, often written as R, Z, is dependent on x and y, both of these variables. So x and y now are independent variables. So two variable functions means that there are two independent variables. Okay, so it's not about how many dependent variables, it's about how many independent variables there is. And there is one terminology that I introduced here, the region. So it's not just a set. So the domain is not just a set, it's a region. So it's a concept similar to the interval. So when we talk about the interval, we talk about this continuous set of points, right? We're not talking about sporadic set of points. We're taking a continuous set of points. And also, when we take a region, means that we take a continuous set of points. We're not take any point, any set of points. We just take square region or circular region, which are all kind of continuously connected. So that's what I mean by region. If you want more detailed or rigorous definition, you can look at our book here. All right, so let's draw the two variable function. So we're gonna talk about the formulas and other types too, but let's say I want to draw the graph of f equals x squared plus y squared. So this is my formula. And again, if you have a formula, you always need to find the domain to define a function. This is not a function. This is just the formula, assignment rule. Let's say our domain of function is -1 to 1, 0 to 2. Okay. So this is a standard way of writing the rectangular domain, rectangular region, which means that this is the x range, and this is the y range. So in the picture, it's -1 to 1 on x and 0 to 2. So we are taking this rectangular region as our domain. So this is not the graph. So how do we draw the graph of the function? So we need to do the similar thing as we draw the graph of single variable function. We need to plot the point, right? But we cannot plot the point on two-dimensional point because two-dimension is the input. We have another coordinates which represents the value of the function, right? So we go for three-dimension, x, y, and z, and x from -1 to 1, y from 0 to 2. So this is the kind of a shadowy part of our graph, because at each point I want to map a point which is the value of that point of the function. So if this is x comma y, then the point that I really want to draw as a part of a graph is going to have a third coordinate, same as the function value of that function. So I want to collect all these points, but I cannot draw infinitely many points. So I need a clever way of doing this. What can I do? So you have probably seen the graph of a surface. I can draw in a board like this, but also you can see the computer image of a surface. What do you think computer did when they draw the graph of a surface in 3 dimensions? How do they draw the graph of a surface?
First draw a line,
Yeah.
function in piecewise, and then those like change them on bit axis,
Yes.
depending on the equation.
Yeah. So you want to do basically the same thing here in the single variable case. You want to draw the lines that lies on the surface, like this. So some graphs, some visual graphs have a nice gradient in color, but let's try with the very primitive way. So ironically, there's some funny thing I'll just mention about this. So if you want to draw something on the plane, you cannot draw a two-dimensional thing. Well, you can draw the boundary of a two-dimensional thing, right? But you cannot do anything on inside. So in two-dimensional plane, what you can really distinguish is the line. You can only distinguish one line to another, and then connect these lines to make a shape. So how about in 3 dimension? Oh, yeah, that's something I always try to. Yeah, so if you see this screen, then it's recording this board. So if you don't see this screen and I'm keep talking on this board, let me know. So switch it. I can switch it. So So if you want to draw something on the 3 dimension, what you really need is drawing a line. Like, for example, if I have a surface like this one, right? Then what I can, if I just put the points on the 3 dimensions, this is not really 3 dimension. You see, what I draw is on the 2 dimension. I draw the projection of 3-dimensional figure. If I put the points, lots of points, what happens is I cannot distinguish which is behind and which is front. Right? I will get some kind of figure like the weird shape like this. So I cannot distinguish what that looked like. Right? So in fact, even if you draw the 2-dimensional thing in the 3 dimension, you need to draw the lines. So here, let's draw the lines of these curves. So how do we draw the lines of these curves? How do you draw the lines of the curves? You can't draw the curve in computer. It's impossible because curve is an infinite set of points. So you can mimic, looks like, you can make your line segment look like a curve, right? So if you have a curve, then you can have lots of points on the curve and connect them with line segment, right? Look like a curve. So here, how would you set up the line segments on the surface so that it will look like a curve on the surface? So if you have so let me draw a nice real picture of this function, a graph of this function. So this is your x-axis, and let's say this is your y-axis. So don't worry about the range here. So right now, what I can do is take lots of horizontal and vertical lines on the 2-dimensional region in xy plane, and then lift these lines up into the surface, and then try to draw the line segment on 3 dimension. That's one way to do it. So let's try that. Let's try and see what happens. Okay, so here, okay. So first, I want to set a horizontal line, which means that I pick a single y in the range of 0 and 2, and then make lots of points from -1 to 1 for x-axis. Okay. So let's first put x and y as a length space from -1 to 1. Let's take 10 subdivisions. So in order to take 10 subdivisions, I need 11 points, including the first and end points. And for the y part, I need this. And okay, so here is the order. So if I want the horizontal lines, then I have to change my y value from 0 to 2 by tenths of 1. So and then change my x from -1 to 1 by tenths of 1. So pick y value for range of 10, range of 11, sorry, so 11, and y value is the y value. So I can do it a little bit better, but let me put it this way. While also I in the range of 11, x value is going to be, oh, I don't need the x value, right? So just need this. And then I want to draw, so if I pick a point in here, so if I put, let's say, the first y values in the range, and I picked all these values. So these all values are 2-dimensional points. I have all 2-dimensional coordinates. I want to lift them up to the 3-dimensional space by taking the z value by this. So I need to define the function, two-variable function, f equals to lambda. And input is 2, the x and y, and the x squared plus y squared. So I want to input x and y as an array because I have a point as an array. But now my y value is constant, so I can take, let's say, yy to be linspace, ones like x, and multiply y value. You see, ones like means that it gives me the array of the same shape as the array x, but the entry of that array is all 1. So then I multiply y value, which means that this could be a matrix or vector, whatever that is. Since all the entries are 1, when I multiply this scalar, y value, then all the entries will become y value here. So that's yy. I don't want to use the same y, although I use the same x and y because it's only used inside the formula of the function. It's okay, but the outside, you cannot mix, you cannot reuse the variable. And xx is just same x. And let's plot. Oh, by the way, so since this is a three-dimensional figure, I cannot use plot here. I need to do something special here. So if you want to draw the three-dimension, I think we did before, but you had to make an axis with projection of option 3D here. And then when you want to draw something, plot. And since this is 3-dimension, it requires third input, which is the array of z-axis. So z-axis, let's say zz, is computed by input x and y, x lists of points, lists of x coordinates and lists of y coordinates. So putting f, and you get the same size array of consists of z coordinates, and you put z here. All right, so if I do this, let's see what happens. Let's see. Figure.
Professor,
Yes.
I think it's
Sopla. Ah, yes. Thank you. Okay. Y var y. Oh, sorry. J. It's J. And okay. I think I don't need this. Sorry. So I need this only. Okay. So for every j, for every y coordinates, I take all these x coordinates lists and then lift them up to 3-dimension and then plot this. Okay, so all the colors are different because I took this each line as a different plotting here. So every time we draw different lines, Python automatically sets the different colors. So that's why it looks like a gradient color. So anyway, what you see what I'm doing here. So in the Python 3-dimensional figure, this one is x-axis, this one is always x-axis, and this one is y-axis. So this one is z-axis. So at every y, you get the coordinate of x changes from -1 to 1, and z coordinates changes from according to it. And then this is the kind of figure. This somehow gives the shape of a surface, but not enough, right? So let's draw another line. So here you can do almost similar. So in this case, I'll change the index so that you don't confuse about. So now to draw another directional lines, I need to change the x coordinate first, and then according to that x value, I want to set the x-axis to fixed in this value, and y is just y, and same for z because it's the same formula, and plot it again. So when you do this, you can see there is a nice pattern of lines that are intersecting together. They're not, they're not above or behind. They're intersecting each other whenever they have the crossing here. So you can now see what the surface might look like. This is basically what the Python or other visualizing program do when you ask them to draw the surface of a function as a graph of the two-dimensional function. So there's an easy way to do it. I'll show you this. So we use the same function, lambda, x and y. And I want to set the mesh grid. So here, you don't have to draw this one by one. You can do it in a different direction, or you can also think that these crossing, the intersections, when you project it onto xy plane, it makes a grid of two-dimensional plane, right? So you set up the grid points by using the mesh grid. Let me put it up here, mesh grid, and now you put how many divisions you want to put in x and y axis. So for example, if I want -1 to 1, which is the range of x, to be split it into 10 subdivisions, and 0 to 2, split it into 10 subdivisions, and put them into the input of mesh grid, then it gives you 10 by 10 mesh grid. So actually it's, if you take it inside of the rectangle, it's 10 by 10, but as a point-wise, it's 11 by 11. Anyway, so that coordinate at each of this mesh grid is computed by plugging in this array of x and y coordinates. By the way, since mesh grid is two-dimensional array, it's a matrix, but you can also put the matrix inside of this variable x and y. When you take the square, it's not matrix square, it's the entry-wise square. And then you can use the function called plot surface and draw the graph of a surface. X. Let me do it again. So here, copy paste again. I have to load this again. So here, yes. So there's a thin line, a white dot, that indicates where this mesh grid are mesh grids are set inside of the surface. So any questions? So we're gonna draw lots of other surface today, and show what? Code, yeah, so code. Any other questions? All right, so try out these ones. So let's see. So let me show you another one here. So if you have a function whose value is just the real number, then the graph of that function, so this is the graph of function f, is the collection of three-dimensional points where the last coordinate z-axis is determined by the first two coordinates and the value of function. But now, let's talk about other type of functions. So for example, if you have a function that maps the two-dimensional point to three-dimensional points, that means your coordinates in three-dimensional points are determined by both of u and v, which are independent variables. So for example, here is one. So if I set my SUV to be hyperbolic sine, cosine v, I'll explain what hyperbolic sine is, and hyperbolic sine u and sine v and v. Then, so this is x coordinate, and this is y coordinate, and this is z coordinate of three-dimensional point as an output. So how would you draw the graph of this function? If you simply follow the same method here, then you need two variable and three variable put in all together in big space, like 5-dimensional space. But you cannot draw 5-dimensional space. I mean, you can draw in your head, maybe, but you cannot visualize in this 2-dimensional picture. So 3-dimension is it's the highest dimension we can visualize in this 2-dimensional figure. Even in 2-dimension, we are actually looking at the projection. Anyway, so you don't want to put these 5 variables in one big screen. So in this case, the best way to draw the graph is just draw the image of the function, just the codomain of the function. So you just want to take x and y and z as the coordinates of 3-dimensional points and draw them, right? How would you draw them? So you imagine that there is a UV plane here, and then you have XY plane, XYZ 3-dimensional space, and there is, so let's say this is UV inside, so let me give a domain of U and V. So it's from -1 to 1, 0 to 2 pi. Okay, so here I had an open interval, and this is closed interval. You see what it means, right? Raise your hand if you don't know the meaning of this parenthesis and bracket. Everyone knows the meaning of this parenthesis and bracket, right? You don't know it? Okay. So I should start from beginning then. So let me just give a quick definition. So here, if I have A, B with a bracket, then we are talking about the set of all points from A to B, including A and B. Okay, so it's including the endpoints. If I have 1 on the left is parenthesis, but on the right is bracket, then I'm taking the set of points without the left end, but including the right end. So the bracket simply means that we include the endpoints. So you can also talk about A bracket B parenthesis and A parenthesis B parenthesis. For example, A parenthesis B parenthesis is all the points from A to B, excluding these two endpoints. So anyway, so let's say this is our interval. So how does it look like? So U is running from -1 to 1, but not including -1 and 1. So it's kind of a dot line here. And also V is from 0 to 2 pi, 0 to 2 pi, but it includes the endpoint. So you can put the solid line here. So it's somewhere inside this box. Okay. But now I want to draw the graph of it only by the image points. So you do the same thing as we did for the graphing the 2-dimensional function in the first example. I take the horizontal and vertical lines inside my domain, and then see where these lines are mapped to in the 3-dimensional space. So for example, let's pick this one, the top one, maybe go somewhere here, and the bottom one maybe somewhere going I don't know, maybe here. I don't know. So anyway, so and also, what happens to the vertical ones? So even if you didn't want to put the vertical lines on the left end and the right end, if you really just want to draw something, unless this points on the left and right doesn't have a value of the function, you can throw in this left and right end, even though in mathematical settings it's not included, because just to make sure that it's there to indicate that it's the endpoints of this left and right, you can just throw in these lines. So in Python, you have to make adjustment. You have to compensate whether you really want to. Okay, so here's another problem. So I didn't record the board here. So yeah, so I don't know what to do. I mean, if I could also make mistake, always make mistakes. So and let me explain again. So I want to draw the graph of this function by taking a point, taking the lines on the codomain space. Okay. So by the way, so what's the sine, hyperbolic sine? So hyperbolic sine, just to remember the definition. It's the definition 1/2 exponential x minus exponential minus x. Okay, just the definition. So the reason why it's hyperbolic sine is because it follows a similar formula as the sine, and it has a deeper meaning, more than that. But anyway, so let's try to draw what happens there, and then let's see what it really is. So you might think, oh, maybe it's too geometric, and it is true that multivariable calculus, you want to do good at multivariable calculus, you have to be good at imagining these three-dimensional figures. So that's why I'm trying to draw this. So here, so let me do it a different way. So I'm going to define U as the length space between -1 to 1, and V to be the length space between 0 to 2 pi. So pi is stored as a constant in the NumPy package. So I used np.pi. And then I'm going to define S as a two-variable function whose value is three-dimensional points. So I need to output as a three-dimensional, it's an array, NumPy array, with the three coordinates point. So first coordinate is sine, hyperbolic sine. So hyperbolic sine U times cosine, right? Cosine V. That's the first coordinate. And the second coordinate, same thing, but instead of cosine, I have sine. And the last one is just V, okay? So I break the line in order to make it clear that this one is first, second, third, x, y, z coordinate. And then my function is called S, and let's plot it again. So axis, PRT, figure, add, subplot, projection, 3D, and I'm going to plot surface. Now, before I plot the surface, what I need to do, same thing as I did in the previous picture, I need to make a mesh grid of my domain of UV plane. So I only have UV as a one-dimensional line segment, a one-dimensional array of subdividing a one-dimensional axis. It's not enough. I need two-dimensional array of mesh grid, of mesh points. So mesh grid of U and V. So UV is just replacing these arrays. And then U is, okay. So what happens when okay, so let me write again. What happens when I compute S with this U and V as an input? So I put U as a two-dimensional array of U coordinates in mesh grid and V coordinates into here to get the a two-dimensional array of Z coordinates. So you see, UV are two-dimensional, UU and VV are two-dimensional array of U coordinates and V coordinates of this mesh grid in two-dimensional plane. according to that coordinates, I want to find out the set coordinate of each mesh grid point. So when I do that, I don't preserve UU and VV as an output as S. So S has an output of completely new coordinates, X, Y, Z coordinates in the totally different three-dimensional space. So I want to use all of this, all the information here, and let me just print out for you. So if I, let's say, have 3 here, so that's the most extreme case here, which means that I only have 2 subdivision on each each interval. And if I print out this, I have this. So what you get is, so 3 by 3 matrix basically. So it's the first one is about x coordinate, second is y coordinate, and z coordinate. And the first coordinate is x coordinate consists of x coordinates of x coordinate of the points in three-dimensional space according to the mesh grid of the domain. And the same for y coordinate and z coordinate. I want to take all this in account to find out the shape of our surface. Now let's drop this number to make it finer here. So I have to put this one, and all together, but there's an easy way to do it. Add, plot surface S. So you put the asterisk here. So asterisk means that also in Python and most programming languages means that you want to look up the memory address, not the value itself. So you go to the memory address and then see where XYZ is. I'm sorry, what's happening here? Plot, not PLT, sorry, X is plot surface. Okay, so here is the figure of your surface. So you can look at the code. So what does this figure look like, this surface look like? So it's a kind of a spiral, right? So you can imagine that this surface is created by the trajectory of a curve or line segment spinning in a certain spinning angle, and then its height is moving from bottom to top in a certain speed. So it's make up some kind of spiral figure. So it's called a helicoid. So why is it helicoid makes sense? By looking at the formula. So I want you to get an idea. I mean, everyone can see the figure and see what that looked like, but you have to understand how could this figure is possible? Why this figure? Where this figure comes out? Even if you're looking at this formula. So you can see that there's something multiplied cosine, something multiplied sine, and v. So v is the height, basically. So v is changing from 0 to 2 pi. So its height is changing from bottom to top. And you have a cosine and sine multiplied. Is it something do you have any similar thing in mind when you see this cosine and sine? When you want to draw the circle, if you want to draw the circle, you need cosine and sine, right? Because cosine and sine is the x and y coordinates of the circle. So you can imagine that this is kind of a circle, but you can see that the radius part, something that has to be similar to radius, is changing as sine hyperbolic u. So what does hyperbolic sine look like? So as I said, the formula is there. So if hyperbolic sine, what is hyperbolic sine 0 look like? What is this value? It's 0 because hyperbolic sign is the subtraction of exponential function with exponential minus. So you have 0, and what happens when you have x bigger and bigger? So hyperbolic sine x is exponential x minus exponential minus x. When x gets bigger, this gets smaller to 0. This gets larger and larger, so it goes infinity, right? So how about this? When x goes to negative, so then exponential x becomes smaller and smaller, and exponential minus x becomes larger and larger, but it has a negative sign, so it goes to negative infinity, right? So this is the graph of the hyperbolic sign. And you can imagine that the radius is actually changing from minus value to plus value when you move your u from -1 to 1, right? So if u, so this is now u, considered as u, -1 to 1, then the value of hyperbolic sign is changing from some minus value to some plus value, right? So if it's plus, well, it's obvious. If you're looking at your x, y, z space from top and you really look at the xy plane, then you can imagine that in a certain angle v, you can say radius is changing from 0 to positive direction to up to here. But then if the radius sine h u is changing to negative, then you can see that it's moving backward here, right? In the same angle. So you have a line segment right here at each v, at each height. And then when v is changing, you change the rotating angle. So you're moving it in a one radian speed. And also you're changing the height, right? So you have this road, this line segment, and it's turning when you're looking at the three-dimensional figure from top. But in actual three-dimensional, what happens is that this line segment, height of line segment is actually changing too at the same time, so that you get this figure. So you should think that this makes sense even for this shape itself and also the formula. So let me show you another one. Let me show you another formula and then draw for yourself what it looked like. I'll give you time to do it. So if you don't have a computer right now, you can ask for people next to you to borrow it, or you can watch them how to do it, how they're doing it. So here's another example that when UV, so again, here, let me take this -1 to 1 and 0 to 2 pi as a domain. And so in this case, instead of hyperbolic sine, let's take a cosine, hyperbolic cosine, and cosine v, hyperbolic cosine v. Let me erase this. And sine v and v. So what is hyperbolic cosine? This is 1/2 exponential u plus exponential minus u. So draw for yourself and then see what it gets as a surface. So you can change a little bit to your code. So only sine h changes to cosine h. And let's see what happens here. So instead of sine h, I change to cosine h, and everything else is same. Let's see. Oh. Cosine h. Oh, let's see. I see. Yeah, but this is the figure. This is the figure according to the formula that I just gave you here. That's not really what I intended to, but yeah. So anyway, this is the figure you should get when you type in the formula, this formula. Well, let's use this formula. Let's change a little bit of this formula. Instead of v, let's put u. See what happens. So here, let's change to u, and yeah, so this is what I intended to. So this is called catenoid. Okay. So it's a cylinder, but the radius of cylinder is different. It's changing by its height. And why does that make sense? Why does that make sense according to the formula? So if you see the formula here, the radius is following the cosine hyperbolic, and the v is kind of a rotation angle, and the height is not dependent on the rotating angle. It's dependent on the radius, right? So u is here. So what does cosine h look like? The graph of cosine h looks like this, right? So it never gets 0 or negative, so always bigger than 1. So when u is changing from -1 to 1, the radius is changing from a little bit higher than 1 and down onto 1, and then go back onto bigger than 1, right? That's the radius. And you can imagine v is making kind of this rotation here. And the last one, u, which is the height of this surface, is going to be determined by this axis, right? So you're kind of rotating again, and then put this axis, which is u-axis, upright to make it as a z-axis. So that's why you get this catenoid figure right here, right? That makes sense? So let's draw a little bit different ones. So let's see. Let me write down 2 more equations. So first, torus and Möbius band. So it's interesting to see you can even draw 3-dimensional objects in the as a surface. So here, the torus has 2 independent variables, theta and phi, and I'm gonna introduce a different symbol, r and small r, which is going to be just constant, but you have to choose it by yourself to draw a real torus here, and r plus cosine phi sine theta and r sine phi. Right, so that's and theta phi is from 0 to 2 pi and 0 to 2 pi. And then Möbius band is u theta, where r plus u cosine zeta over 2. So this R is also constant. And cosine zeta. And same thing, R plus U cosine zeta over 2 times sine zeta. And the last one is U sine zeta over 2. Okay, so here, U, let's see, U is, it really depends on how big your R is. So I'm going to take a minus 1 to 1 here. And zeta is from, so U and zeta, sorry, so U and zeta is minus 1 to 1 and 0 to 2 pi. And I'm going to assume that R is bigger than 1. Okay? So here, R is bigger than R, small r. So make sure, so you don't have to remember this formula. All I want you to do is just have an exercise of drawing these big figures and then see why this formula makes sense according to your result. So I'm going to draw the Möbius band just for now. So let's see. So we have U and zeta. So let me take UU and TT as a mesh grid. And U is from minus 1 to 1. And T is from 0 to 2 pi. And what's my function? So S is UT2 first. So I need to set my R. So let's say R is 2, I think. 2 might be okay. So R plus U times cosine T over 2 times cosine T. That's the first one. So I think, okay, so there's a problem. So numpy cosine and numpy cosine. And then the same thing with sine, right? And then the last thing is U times sine T over 2. So I want to draw it. So axis. So I forgot numpy sign here. And axis plot surface SUU TT. Okay, so what's the problem? Subplot. Okay. Oh, I think I should make R bigger. So let's make it R5. I think it doesn't matter. So I think it's problem about equaling axis. Axis equal. Okay. All right, so that's better. So this is the code. And let's see the figure. So can you see the figure correctly? So it's not really representing well about the important characteristic of Möbius band, but anyone who heard about the Möbius band is not a cylinder. It's not cylinder-like surface. It's somehow you cut the cylinder in half and then you put the other end, two ends, two boundary in a 180 rotation. So when you move along the surface and then it kind of flips around and then comes back to the point again. So it's going to be introduced later when we talk about the surface integral, because this is the typical sample which doesn't have orientation. But you have to know why this happens by looking at the formula itself. Here, to look at the formula. So what does R means? Big R. What does big R means? So this figure has the origin at 0. The 0, 0, 0 is the origin. R is the radius from this origin to the center line of this Möbius band. That's R. And what does this u times cosine theta over 2 means? So that means, so here, so u times cosine theta over 2 means you want to change your radius a little bit by this amount, u times cosine theta over 2. And u is changing from -1. It's same as the helicoid when we had radius from +1 to -1. You want to change from here to here. But the angle of rotation of your the big radius is not t, it's t over 2. So when theta is changing from 0 to 2 pi, your radius is only changing from 0 to pi. So what happens when your cosine is changing from 0 to pi? So it's from 1 to -1. It's not coming back. So when you make a full circle around maybe a span around the center line, center rim, then your radius is from changing to 1 to 0. In some sense, it was upright in the beginning, but at the end, it's flipped because it's -1. Your direction of your radius, the direction of your line segment that determines the radius is now flipped after having a one rotation. So that's why you have a flipped the one end of the Möbius band and glued it to another one. So I'm giving you the core ideas, but if you don't understand it, you have to think of on yourself. So let's draw another one. So now it's not really a two-dimensional. So it's not really a two-dimensional curve or surface. It's not two-dimensional surface, but I want to draw a curve. So you can also draw the curve as this similar format here. So it's called the parametric curve. Let's say I want to define my curve C as something like cosine t, np cosine t, and np sine t. So you know what this is. This is the circle. So let's say t lambda, okay, np length space from 0 to 2 pi, then PLT plot, and cosine t, ct, and having this will get you a circle, right? So here, I'm not drawing the domain axis of the function c. So function c has a domain who's represented by variable t, and the interval is 0 to 2 pi. I'm not drawing that axis in this two-dimensional figure. I'm drawing only the x and y coordinates of the image of this function c. So this is not, c is not single variable function. It's called multivariable function. It's actually called the parametric curve, but it's not called as a single variable function, even though it has one independent variable. So you have to distinguish that when you call n variable function, it usually means that it has n independent variable, which n is bigger than 1. But a single variable function only applies when you have one independent variable and one dependent variable. But so this is not single variable function. The reason why in the picture it doesn't look like a circle is because the axis is not equal. The axis scale is not equalized. So we have axis equal, then you can see actual circle. So even in here, it looks like a curve, but it's really not. So there's no curve in a screen because screen itself is just discrete grid of the light source. So it looks like kind of a circle, like a good curve, but it's really not. And the way we draw the circle, this figure, is not really a circle. It's just lots of polygon. I mean, polygon with lots of vertex, 99 vertex here. Okay, so let's draw another one. What shall we draw? Okay, so how about we draw some quadratic equations? So here I'm going to introduce polar coordinates. Okay, so I cannot forget this. Let's see. So let's look at the polar coordinates. So when you have two-dimensional points, x, y, you know that this xy can be represented by the radius from the origin to that point and the angle between this line and x-axis, right? So this can be also represented by r and theta. The relation between these four variables is x equals to r cosine theta and y equals to r sine theta. So for example, if you want to write down the equation of a circle like this one, it has the origin at center at the origin and the radius at 1. You can also write this as r equals to 1. It's the same equation in different expression. So in the xy coordinate called Cartesian coordinate, you can write the circle in this equation. In the polar coordinate, this is the equation. Now, let's talk about the parabola. So what's the definition of parabola? I think this is something you learn in the high school, right? So you have a line, I forgot the name of this line, whatever, and you have a focal point. Let's say your focal point is 0, 0. What's the definition of parabola? Have you heard about the definition of parabola using these two lines and focal points? No? No? It's not, they're not teaching anymore about the parabola? No? Okay. So usually what you'd say, you imagine what about the parabola is the graph of a function, something like this, right? You know that the graph of this y equals to x squared is called a parabola, right? So something like this, parabola. But parabola is geometrically defined that this way. So it's a collection of all points whose lengths between lengths of point to the origin to and lengths to the line segments are equal. So if you collect all the points that has the same length between these two line segments, you get the parabola. So here, when you take a line which is perpendicular here, then it has to be the middle point here. And you also have take here, same line point. So this is the parabola. So let's say we call this line L. And the parabola, definition of parabola means that we have PL and PO, which is the focal point here, O, is equals to 1. Could you raise your hand if you have seen this kind of definition before? Okay, so not everyone. It's surprising. So anyway, let's write down this equation in the polar coordinates. How do you write down that? So remember that where is my x and y axis? It's right here. This is my xy axis. Okay, this is x and y axis, and I'm not writing down in the Cartesian coordinate. Remember, I'm using polar coordinate. So the r, the radius of that point, is this line, the length of this line segment. This is r. Okay, so how do you take this line segment? What's the length of this line segment? Let's say, okay, I need one more information where the line is. Let's say my line is at x equals to d. So the total distance from the focal point to the point here, which is perpendicular, is d. So what's the length of this line segment? Yeah, d minus r cosine theta. Yes. So I want this to be equal to r. That's my definition of parabola. So r equals to d over 1 plus cosine theta. So how do you draw this in a graph? So you have to draw with xy coordinates. I mean, that's what we have to do. So x coordinates is r cosine theta, but r is determined by this formula. So I just replace r by this formula. We have d over 1 plus cosine theta, and y is r sine theta. So it's d 1 plus cosine theta, sine theta, right? So what will be the range of theta in this case? So I can certainly have points here in the middle of this O and L. So in this case, theta is 0. But can I move my theta all the way over this pi? Can I? So you remember that cosine theta has a graph like this. So when theta is 0, it has 1. But when theta is pi, means that I'm moving my angle all the way up to the negative direction of x-axis, then it becomes negative 1, right? So what happens to the numerator and denominator? It's going to become 0, so we cannot have a 0. So you can have theta as close as pi, but you can't get to the pi. So that's why you get your parabola is increasing and increasing further and further. You can almost get to the edge here, but you're not gonna find a value or a point on the parabola when you move on this direction, because there's no parabola intersecting here. So let's try to draw it. Let's see whether it really gives me the parabola shape. Okay, so here again, it's not the surface, it's a curve, two-dimensional curve. So numpy array. So I cannot, let's say minus pi to pi is ideal, but I cannot really get the minus pi plugged in. So I'm going to set the small number added here, EPS representing epsilon here. So epsilon is, let's say, 10 to the minus 2, okay, 0.01. Okay, so I'm gonna have this, and EPS, minus EPS. And then what is my x? So x is, okay, so I need to set my d first. Let's say d is 1. My d is also 1. So d over 1 plus cosine t and cosine t, and y goes to d over 1 plus numpy cosine t sine t. And this is two-dimensional plus, so I don't need to projection 3D. Okay, so this is the figure. Okay. So you can see that this parabola is quite straight all the way up to here, but it changes the direction at the focal point, around the focal point. The reason why it looks almost straight is because I draw it in a big scale, because I wanted to draw with a big angle. So if I want to just draw in a small angle, let's say I want just draw it on the 3 pi over 4 degree, then I will get the nice figure of this parabola, 3 pi over 4, 3 pi over 4. Then yeah, it really looks like a parabola, even if I make axis equal. Looks like a real parabola. So where's my focal point? The one focal point. It's right here. It's not on the parabola. Don't confuse about the formula that I just gave in the first hand. The y equals x squared has a tip at the 0, 0, but this one has no tip on the 0. The tip is not on the origin. The origin is the focal point. Okay, so focal points here. So if you want to write the formula of this parabola in Cartesian coordinate, you're not going to get similar to y equals to x squared. It's a bit different. All right, well, let's do a little bit one more thing and then let's finish it. So you see, there are three types of quadratic curve. One is parabola. The others are ellipse and hyperbola. So where did I put? Oh, here. So yeah, there are more. So it depends on what the ratio is. So if parabola is when you have this, so E is called eccentricity. So E equals to 1, and ellipse and hyperbola is when you have E not equals to 1. So let's see what happens. So but the situations are almost same. You have the line L, and then you have a focal point, which is the origin. And let's say you have a ellipse. So its ellipse is like squeezed circle. When do you get kind of the definition of this ellipse is that you have a point P and a point at the line segment that connects the point to the line here and in the perpendicular way. So if you compare the length of the line segment from 0 to P and P to L, which one do you think it's longer? The first one or second one in the ellipse? If you want to make an ellipse as the same definition as below, so the ellipse is a set of points whose ratio is always constant, E, but if you really want to make an ellipse, does E has to be less than 1 or bigger than 1? Bigger? So bigger means OP is bigger, OP is larger, right? Yeah, in fact, actually, you have to have E smaller, right? E smaller. So let's see. I'm not, well, I cannot, maybe I'm wrong, but we can try to draw it. So let's do the same computation here. What is OP? It's R. And what is PL? It's R minus R cosine theta, and this is E. And that's the equation of the parabola. So this is the equation of ellipse. And then this R is now equals to RE minus RE cosine theta. Is it right? No, it's not R, it's D, right? So D, okay. So DE here. So R is DE over 1 plus E cosine theta, right? So let's try to draw it. Okay, so I also forgot to change the screen. Anyway, so let's draw it. Let's put another E here. So E, let's see, 0.5. Let's say make it less than 1 and see what happens. And D times E over 1 plus E times cosine. And Y is also D times E, E times cosine, and sine and cosine. Let's see what happens. Okay, so it looks like a ellipse, right? So the reason why I don't have further in here because I just draw the theta from minus 3 over 3 pi over 4 and 3 pi over 4. So if I change this to minus pi over 5, then I think it's going to make a full ellipse. Minus pi over pi. Minus pi over, sorry. It's minus pi over pi. Yeah, so it's ellipse. Well, it looks like a circle to me. Then you can change this E to be a bit closer, I think. 8. Let's see. Yeah, then it looks like ellipse now, right? The reason why you have a breaking on here is because you have a larger area. I mean, you're looking at the angle are evenly distributed here. So if you make an angle evenly distributed, so and the focal point is not here, focal point is here. So if you split the angle in here, then you get a larger difference at this part because the radius is bigger. So ellipse is when you have eccentricity less than 1, and hyperbola is when you have eccentricity bigger than 1. So let's try that. So hyperboloid will be actually looks like a parabola, but it will not. It's the same thing. So I should be careful about this pi. So let's just pi over 2 instead. Okay, so pi over 2. Yeah, so we can see that this is the part of hyperbola. So if you go further and further out, then it goes infinity. It's not going to close out because you have e bigger than 1. So what happens when you have e bigger than 1? Your cosine, of course, cannot be negative 1 or 1 because it will be negative 1, then it has negative value. Or when it gets negative value, it will pass the 0 so that you have a point where you have a 0 in the denominator. That's not possible. So you can have a theta only when you have, until you get e cosine theta less than 1, right? That's a negative value. So you have a certain range of theta to be able to draw this hyperbola. All right, so if you have any questions, let me know, and we'll see you on Wednesday.